Okay, so this video is going to be starting Chapter 8, which covers covalent compounds, bonding theories, and molecular structure. Now, we're not going to cover all the sections in this chapter. Specifically, we're going to omit molecular orbital theory at the end of this chapter. In past semesters, I've covered this, but given the current circumstances and the fact that it's not, as far as I know, on the final exam, it's certainly not on the ACS final exam, we're just not going to cover that for what I hope are obvious reasons. That said, if you think you're going to take organic chemistry at some point, which I know many of you probably will, I definitely recommend reading over that section for your own benefit because it does come up in higher level courses like that. But for now, we'll just go ahead and get into it, starting with the VSEPR model. So the valence shell electron pair repulsion model, which is abbreviated VSEPR, is a simple enough model to understand. It basically just relies on the fact that electrons repel each other, and so if we look at the central atom in a Lewis structure, like the kind that we drew in the previous chapter, and we take into account the fact that any atoms it's attached to have electrons due to both bonding and potentially lone pairs, and there's also lone pairs on the central atom, they're going to try to get as far apart from each other as they possibly can. And so the electron pairs in molecules, both lone pairs and bonding pairs, basically try to spread out in 3D space as much as is physically possible. And again, that's just due to the fact that all electrons are negatively charged, so they repel each other. So what we're going to do, essentially, is starting with electron dot structures, which hopefully you've mastered from the previous chapter, we're going to take those and analyze them, specifically analyze the central atom, to predict what the arrangement of what your book calls charge clouds, some other references call electron domains, by assuming that all of those charge clouds are oriented in space as far away from each other as possible. And again, charge clouds here are electron pairs, whether lone pairs or bonding pairs, and the atoms and their electron shells that are attached to that central atom. So we're going to consider several different circumstances from kind of the simplest, which are where the central atom is surrounded by two charge clouds, all the way up to situations where the central atom is surrounded by 6 charge clouds. So we'll cover 2, 3, 4, 5, and 6 charge cloud examples. So starting with 2, on your screen you see a couple of molecules, first carbon dioxide, second hydrogen cyanide, that have a carbon atom in the center of a molecule, and that carbon has 2 charge clouds attached to it. And in both cases, those charge clouds are bonding pairs of electrons from the atoms that it's attached to. So in the case of carbon dioxide, that central carbon atom forms 2 double bonds to 2 oxygen atoms, each of which have 2 lone pairs. And in the case of hydrogen cyanide, the carbon has a triple bond to a nitrogen, which itself has a lone pair, and it also has a single bond to a hydrogen, but those are still just 2 charge clouds. So keep in mind here that when we count charge clouds, we're not counting the number of bonds between 2 atoms. It's just the number of atoms that the central atom is attached to, and then as we get to more charge clouds, we'll also count lone pairs. But we don't count double bonds as 2, and we don't count triple bonds as 3. But in the case of 2 charge clouds, things are pretty simple. The furthest away 2 things can be away from each other in 3D space is 180 degrees. So all these molecules are linear. They're oriented with all the atoms in a straight line in 3D space. And so the bond angle, the angle between the oxygen-carbon-oxygen bond in carbon dioxide or hydrogen-carbon-nitrogen bond in hydrogen cyanide, are both 180 degrees. And you will need to know the terminology for the different orientations. So for instance, with 2 charge clouds, these are linear molecules. You'll also need to know the approximate bond angles, which for all but one case are all fairly simple to remember. So they're all like 180 degrees or 120 or 90, with the exception of 4 charge clouds, which we'll cover later. So we'll move on to the 3-charge cloud example next. So for these examples, we can look at a couple examples. The first one is formaldehyde, CH2O, which is a molecule that we drew the Lewis dot structure of on a slide in Chapter 7. And we'll also look at sulfur dioxide, which has only 2 atoms attached to the central sulfur atom, but it still contains 3 charge clouds because it's got a lone pair on the sulfur atom if you draw out the correct Lewis dot structure. So looking at formaldehyde first, our central carbon atom is attached to 3 other atoms, 1 oxygen and 2 hydrogens. And again, for our purposes in terms of counting charge clouds, we don't need to worry about the fact that there are 2 bonds between carbon and oxygen, just the number of separate atoms that the carbon atom in the center is attached to. Now, if we have 3 charge clouds, the valence shell electron pair repulsion model predicts that all of those charge clouds should be 120 degrees apart, because if you take a 360-degree circle and divide it into 3 equal pieces, it'll be 120 degrees. So everything should be 120 degrees apart to maximize the distance between them. Now, in the case of real molecules, especially where the atoms attached to the central atom are not all the same size, for instance, hydrogen atoms are smaller than oxygen atoms, there's some deviation from the idealized bond angles. Now, you don't need to know, for instance, that in formaldehyde the bond angles happen to be exactly 122 and 117 degrees. You should just know that for a 3-charge cloud situation, the approximate bond angle should be 120 degrees or so. And the geometry around the carbon atom in formaldehyde is referred to as trigonal planar. Trigonal for 3 and planar because all of the atoms lie in the same plane. If you look at the 2 hydrogen atoms and the oxygen atom, they basically form a triangle. If we move on to sulfur dioxide, again, this sulfur atom is only bonded to 2 oxygen atoms, but if you draw out the Lewis structure, you should end up with a sulfur in the middle, 2 oxygens. There's going to be 1 sulfur-oxygen double bond, 1 sulfur-oxygen single bond, and you'll end up putting 2 electrons, or 1 lone pair, on the sulfur atom in step 4 of drawing the Lewis dot structure for that. Now, again, we would predict the bond angle between the oxygen, sulfur, and oxygen to be about 120 degrees, based on the fact that there's 3 charge clouds here, 1 lone pair and 2 oxygen atoms. In fact, let me go ahead and circle those. So we have 1 charge cloud here, and then 2 separate atoms that those are attached to. Now, this example shows us a situation where not only does the bond angle deviate a little bit from 120 degrees, but we can actually predict that this bond angle should be a little bit less than 120 degrees for the following reason. So the lone pair on sulfur is just a region of pure electron density. It's purely negatively charged, whereas the other 2 charge clouds are atoms, and those contain negatively charged electrons, hence they're repelled from the lone pair. But overall, they're charge neutral, at least in most cases they are. What that means is that the lone pair more strongly pushes away the, in this case, oxygen atoms than the oxygen atoms push away each other. And so the bond angle between the 2 oxygen atoms and the sulfur kind of gets squeezed in a little bit due to the strong repulsion from the lone pair on the sulfur. So this bond angle is not 120 degrees exactly, but a little bit less than 120 degrees. And this molecular geometry here is referred to as bent, because the molecule itself in 3D space is this bent shape, as opposed to being a linear molecule in the 3 atom cases we saw on the previous slide. So the 2 geometry possibilities here are trigonal planar and bent. Now we're going to move on to 4 charge clouds, and things become a little bit more complicated here for a few reasons. So first of all, there's more possibilities that we need to consider. Second of all, 4 charge clouds is kind of unique in the respect that with 4 charge clouds, the bond angle is not going to be some sort of typical angle that you're used to, like 90 or 120 or 180 degrees. It's actually kind of this weird angle which is about 109.5 degrees. And that comes from doing some rather complicated trigonometry with tetrahedral shapes. Also, we need to start thinking in 3 dimensions now, because the furthest away 4 things can be from each other in 3D space when they're all attached to the same center is at the vertices of a tetrahedron, which is basically a regular triangular pyramid. So you can see this is like a pyramid shape with a triangular base, and all the lengths are the same. And if we superimpose that tetrahedron onto the 4 red atoms in the central image there, you can see that the carbon atom here is at the center, and the 4 red atoms are on the vertices of that tetrahedron. And again, the bond angles between any 2 outside atoms with the central atom in the middle are always going to be 109.5 degrees, at least as long as all 4 atoms are the same size. So we're going to cover 3 possible examples here. The first is where we have all 4 of those positions around the tetrahedron occupied by atoms. And then we'll also consider what happens if we have 3 atoms and 1 lone pair, or 2 atoms and 2 lone pairs. So as a prototypical example of the first case, where we have 4 atoms and no lone pairs, so that's still 4 charge clouds, we're going to use methane, CH4. Now you can see that the bond angle between any hydrogen, carbon, and another hydrogen is, as predicted, 109.5 degrees. And you might notice that some of these bonds might look a little bit funny. So for instance, this one right here and this one right here. So you might wonder what's going on with that. Now this has to do with the fact that now that we have 4 charge clouds, we need to kind of think about things in 3 dimensions as opposed to just 2. So what this dark wedge means, this one right here, is that not only is this bond pointing down and to the left a little bit in this orientation, it's also pointing out of the screen towards you. So that hydrogen atom, if the carbon atom and these 2 hydrogen atoms right here, if those are both in the plane of the screen, this hydrogen atom would be sticking out of the screen towards you. And the 4th hydrogen atom there, the one that kind of has a dash going to it instead of a wedge right here, this one's pointing behind the screen in addition to pointing down and to the left. So again, this is just representing how those things are in 3D space. So that's what happens if we have 4 atoms. If we take one of those atoms and we replace it with a lone pair, such as in ammonia, where we have a nitrogen, 3 hydrogens, singly bonded to our nitrogen, and then a lone pair, and again that comes from just drawing out the Lewis structure for ammonia, NH3, we can see that we still have hydrogens in 3 of the same places, at least approximately, as we did in methane, but one of those positions has been replaced with a lone pair. And so the result is that we have this molecule here, where you can see the 3 hydrogen atoms are kind of in a plane beneath the nitrogen, and the nitrogen is elevated a little bit from them. And in addition to that, the 109.5 degree bond angle has been contracted slightly to 107 degrees. Again, don't worry about the exact angle, although you can predict that it should be a little bit less than 109.5 due to the fact that the lone pair is going to more strongly repel the hydrogens than the hydrogens repel each other. And so this molecular geometry here is referred to as trigonal pyramidal. Trigonal because we have basically a triangular base from the 3 hydrogens, and pyramidal because it forms a pyramidal shape. The methane molecule is referred to as tetrahedral because the 4 hydrogens just occupy the 4 vertices on a tetrahedron. And if we come over to water here, H2O, we covered drawing this molecule in Chapter 7 on one of the first Lewis structure example slides. And you might recall from that that water has an oxygen in the middle, 2 hydrogens attached to it, and 2 lone pairs. And now that we have 2 lone pairs, the 109.5 degree bond angle is going to be contracted even further, in this case down to 104.5 degrees. And the shape of the molecule is what you see right here. The oxygen's in red, the hydrogens are in white, and this is also referred to as bent, not to be confused with the bent shape that we saw with sulfur dioxide. So confusingly enough, there's two different types of molecular geometry that are referred to as bent with different bond angles, so you will need to remember that. So those are the three situations we're going to consider where we have 4 charge clouds. Let's move on to a situation with 5 charge clouds. Now for 5 charge clouds, we need to be thinking in 3D space again, and in this case the shape is called trigonal bipyramidal. That's the base shape for all 5 charge cloud positions around the central atom. And this shape is effectively 2 tetrahedra, but essentially with one of their faces sandwiched together. So this face right here is merged with the face of the other tetrahedron. And so at the center of that triangle we have our central atom, and we also have the vertices of that triangle, and then one vertex above and directly below the central atom. The positions directly above and below the central atom are referred to as axial positions because they are along the sort of main axis of the shape, and the 3 positions along the central triangle are referred to as equatorial positions. And in this central image in the middle, the equatorial positions are labeled in blue and the axials are in red. And you might notice from that diagram that there's 2 bond angles listed. So indeed there are 2 different bond angles, but they're all pretty normal angles. Between the axial position and any of the equatorial positions is a right angle, 90 degrees. And since the equatorial positions are equally spaced out, and there are 3 of them, they are 120 degrees apart from each other. So if you kind of rotate that and look at the top view, you can see that maybe a little bit more clearly. So there's 2 different types of bond angles you need to consider when you have 5 charge clouds. Now, since the base shape is a trigonal bipyramid, if we have a situation where we have a central atom and 5 atoms attached to it, like say in phosphorus pentachloride, PCl5, all 5 of those chlorine atoms are exactly the same size, and so this is going to be pretty much the ideal molecular geometry compared to a trigonal bipyramid, and so the molecular geometry here is referred to as trigonal bipyramidal. Now, the next one has kind of a funny name. If we look at sulfur tetrafluoride, SF4, in both of these examples they're leaving the lone pairs off of the chlorine and fluorine atoms for clarity. They are there. Each of them has 3 lone pairs, but we're really only worried about lone pairs on the central atom for purposes of molecular geometry. But if you draw out the Lewis structure for SF4, you should end up with 3 lone pairs on all your fluorines. All 4 of them are singly bonded to your sulfur, and the sulfur itself actually has a lone pair on it. So since the sulfur is attached to 4 atoms, and it also has a lone pair, that's 4 plus 1 is 5 charge clouds, so we're still operating from the base shape of trigonal bipyramidal. And the name for the molecular geometry of this is actually referred to as seesaw, and that is in fact the technical term. If you look at the second image of the sulfur tetrafluoride molecule, this one right here, you can probably see that, at least if you use your imagination a little bit, it does kind of look like a seesaw shape. So seesaw shapes happen when you have 5 charge clouds and 4 of them are atoms. And we'll look at 2 more cases. One where we have 2 lone pairs, and a third where we have 3 lone pairs out of a total of 5 charge clouds. So a good example of a molecule with 5 charge clouds and 2 of those are lone pairs is chlorine trifluoride. If you draw out the Lewis structure for that, again, we've omitted the lone pairs from the outside fluorine atoms. They should all have 3 lone pairs. And the chlorine in the center actually has 2 lone pairs. So with the 3 fluorine atoms plus the 2 lone pairs, we've got 5 charge clouds. And notice in all of these examples, and we can go back to the previous slide for you to see this as well. Whenever we have a lone pair out of 5 charge clouds, all of the lone pairs go into equatorial positions, not axial positions. So in the case of chlorine trifluoride or any other situation where we have 2 lone pairs and 3 atoms attached to the central atom, we're going to have what's referred to as a T-shaped molecule, and you can see pretty easily why that's referred to as T-shaped in either orientation there. All 4 of those atoms lie in the same plane, and they form a T-shape with a right angle. And again, both of these lone pairs are occupying equatorial positions. Finally, we'll look at the triiodide ion, I3-1, which has 3 iodine atoms and an overall -1 charge, as an example where our central atom has 2 atoms attached to it and 3 lone pairs. So again, we've omitted the lone pairs from the top and bottom iodine atoms, which should have 3 lone pairs each. And if you draw the Lewis structure, including the fact that we have an extra electron due to the -1 charge, you should end up with 3 lone pairs around your central iodine atom. And as it turns out, since all 3 of those are equatorial positions, we actually end up in a situation that's kind of similar to what we had with 2 charge clouds, where everything is linear. So those 3 iodine atoms exist in a straight line, and the bond angle is 180 degrees. So that's 5 charge clouds. Finally, we'll look at 6 charge clouds, and I need to start off by clarifying sort of what the base shape is here, and specifically why it's called octahedron. And you might be wondering, why is it called octahedral, or based on an octahedron, when oct means 8, and we're talking about 6 charge clouds? And the answer is shapes like that are named not based on the number of vertices they have, but on the number of faces. So a regular octahedron has 8 separate faces, but it has 6 vertices, and it's the vertices that we count when we are actually looking at the positions of atoms. So an octahedron has 6 vertices, and so is the base shape for 6 charge clouds around a central atom. Now, the distinction between axial and equatorial positions vanishes here because both the angle between the quote-unquote axial and equatorial positions and the angle between the quote-unquote equatorial positions are all 90 degrees, which means that if you take the shapes that you see here and rotate them 90 degrees in basically any direction, you end up with something that's equivalent. And so if we look at some examples with 6 charge clouds, of course, a base example would be where we have all 6 of those positions occupied by atoms. So a good example of this is sulfur hexafluoride, SF6. And again, you can see the dashes and wedges representing the 3D positions of some of these fluorine atoms. That sulfur atom in the middle has 6 atoms attached to it, all fluorine atoms, and no lone pairs, so 6 charge clouds. So it's an octahedral shape, since all of those positions are occupied by atoms. Moving on from that, we can look at an example like the SbCl5 2- ion. I'm not exactly sure what the name of that ion is, but it has, if you draw out the Lewis structure, 5 atoms attached to your antimony atom. That's what Sb is, antimony. So your 5 chlorine atoms are 5 separate charge clouds, and we also have a lone pair on our central atom there, our antimony atom. And so that's a total of 6 charge clouds, but only 5 of them are taken up by atoms. We have a lone pair in one of those positions. And you might notice, if we kind of look over at the shape of the ion itself in a space-filling model, that it forms a square pyramid shape. So pyramid with a square base. And so the name for this geometry is just square pyramidal, simple enough. And the last example of molecular geometry that we'll talk about is where we have 6 charge clouds, and 4 of those are atoms. And a good example of this is xenon tetrafluoride. Now, xenon is a noble gas, so you might be wondering, how can we have a noble gas in a compound? And I may have alluded to this previously, but For some of the heavier noble gases, so mostly xenon, and to a small extent, I believe krypton forms several compounds as well. Those are still quite unreactive, but they are capable of forming a few compounds, mostly with fluorine, just because fluorine is so chemically reactive. So xenon tetrafluoride is one of a handful of examples of compounds where we do actually have a noble gas bonded to some other elements. And in the case of XeF4, if you draw out the Lewis structure accounting for the correct number of valence electrons, we have 4 fluorine atoms attached to your xenon and 2 lone pairs on the central xenon atom as well, for a total of 6 charge clouds. Now, the positioning of the lone pairs, remember lone pairs repel each other more strongly than atoms repel each other, so they're going to be essentially on opposite sides of the octahedral positions. So if one is below the xenon atom, the other one should be above the xenon atom. As a result, we end up with a square planar shape. So if you just kind of connect the 4 fluorine atoms here, you end up with a flat square. So this is called square planar in shape. So summarizing that, on these slides, and this table is in your book as well, more importantly, we have all the situations that we just covered along with the names of the molecular geometries and the associated number of charge clouds and how many of those are atoms, how many of those are lone pairs. So you can see on this slide we have the cases of 2, 3, and 4 charge clouds that we discussed, and on this side we have the 5 and 6 charge cloud cases, and all the ones on this table and in these slides are the only ones you need to know. You don't need to know anything with different numbers of atoms than the ones we discussed. You also don't have to know anything about the geometry of anything with more than 6 charge clouds.